We look at a few other theorems, especially the squeeze theorem that I need to explain. I would like us to evaluate some limits. 11 through 32, you can choose anything if you can see it, or I can zoom in with no problems. So I'd like us to pick a couple of problems from here. And then I would like to, of course, look at the absolute value limits, a couple. And then we'll talk about the squeeze theorem. Can you see, or?
21.
Okay, we want to start with 21, perfect. So let's start with 21. Um, 21. So we have limit as h approaches 0 from the square root of 9 plus h minus 3 divided by h. We're asked to find the limit. What is our first thought? What is the first thing we need to do? Always when we're asked to determine a limit. Always. That's when we graph functions. We always have to find the domain. Go back to your notes. What did we do? Every time we were asked, of course, I have no choice. Because what if I plug it in and it's 5? I don't have to do anything. I move on to the next problem. But if it's 5 over 0, I know it doesn't exist. But I have to write either it does not exist or infinity or negative infinity. Well, what if it's 0 over 0? There is hope, but I don't know. I have to plug it in. I know it's a little bit of a contradiction, but please always plug it in. Okay, so I'll plug it in. What do I get? Okay, so it means that there is hope and I should proceed. How do I proceed now? Let's look at the function. Yes?
Do you, I assume, apply one boss, right? Or do you do the differential? But, I don't know.
That's okay. That's why we're here. That's why we discuss it. I don't expect you to remember this at this moment, but you will remember it. So, is there any way I could simplify this function? Is there anything I could do to this function? This is not how we study in algebra and pre-calc. In algebra and pre-calc, we say no radicals in the denominator. But here I have to say that's my only hope. Exactly. Rationalize the numerator.
Is there a special word for that, or is that just what it's called?
That's it. Rationalize the numerator. So let me refresh your memory. If I have 1 over the square or the cube root of 2, I multiply by the cube root of 2 squared and divide by the cube root of 2 squared because this has to be 1. And when I multiply these two, I just get the cube root of 4. But when I multiply these two, can anyone tell us the answer? Exactly, it's the cube root of 2. That's why we multiply by 2 squared. Excellent. So it has to be 2. So this is what we normally do. We don't rationalize the numerator. But this time I have no choice. I have to rationalize the numerator. So can anyone tell us what do we rationalize it by? Notice that I gave you an example here with one factor in the denominator or one term in the denominator. But we have 2 terms in the numerator over there. We have this term. It's 1 unit, and we have this term, which is the second unit. So what would I multiply and divide by?
You multiply by the square root of 9 plus h plus 3.
Very good. So by the conjugate. So we multiply by the conjugate. So if we have a minus b, we multiply by a plus b. If we have a plus b, we multiply by a minus b. Indeed. So that it takes the square root of 9 plus h plus 3 and the square root of 9 plus h plus 3. When I checked earlier today, how are my students doing, and if they watch anything or if they look at the website or anything, I can only say that only one person exceeded the number of hours that I have listed for myself, and that's Mason. You exceeded. I have to get back in there and do something to catch up with you. Well done. I appreciate that very much. Okay, so I copy the limit. Okay, this is one thing that I need to mention all the time. You cannot drop the limit operator until you get the final answer. That's the last time you write the limit operator. When you write the final answer, you cannot drop the limit operator at any point in time. Okay, so now can anyone tell us? Also, we discussed one very important topic last time. If in a polynomial or an expression, maybe I plug in a number and I get 0, then I know that that number, x minus that number, is the culprit that creates 0 over 0. So we'll see what happens here. So can anyone give us the numerator?
The 9 plus h minus 1.
Excellent. Do not drop the denominator, please. The denominator does not go anywhere. I should have asked you from the very beginning, what do you think this is? The difference quotient, of course. Of course. I expect all terms without h to go away, and I expect the h from the denominator to go away, of course. In that particular order, not vice versa. So these two go away. Please write it one more time. So we have h over h, the square root of 9 plus h plus 3. Now you simplify. Please write 1 so you don't think it's 0, please. Now, at this stage, I am going to drop the limit operator. Why? Because I'm finding the limit now. Please plug it in again and tell me what to get. My cheap markers are getting dried out. I'm ready.
1 over the square root of 9 plus h plus 3.
Careful. H approaches 0. H approaches 0. Is that clear? So then the limit is 1 over 6. Before we look at absolute value limits, because I have to refresh our memory on absolute value, maybe we should choose another. Are we ready? Any questions on this problem? Is this okay? Yes? Okay, so.
I like 19.
19? Fine. I was expecting maybe 28 because it's a difference, but 19 is fine. We can do both. It doesn't matter. If you pick 19, I'm sure you picked it for a reason, so let's also work on that. So in 19, we have, it's also in red, so why not? Let's do 19. X plus 2 divided by x cubed plus 8. And it proves my point that I just discussed a minute ago, so why not? It's a good one. Okay, so I'm asked to find a limit. What do I have to do first? Always mandatory, forever. Good. And I'm hoping for what? I'm hoping for 0 over 0. Let's see if it's 0 over 0. It is. Okay, now, in this particular example, we can discuss that theorem from last time. So, the numerator is a polynomial, x plus 2. The denominator is a polynomial, x cubed plus 8. In the numerator, I plugged in -2 and I got 0. In the denominator, I plugged in -2 and I got 0. So what does that mean for sure? That both polynomials must have a factor of
2. -2.
x plus 2. So keep that in mind because why? Why is it plus? Look at this. Okay? So the factor must be taken out. That's the culprit. That's the quantity that creates 0 over 0. I want it out. Does it mean that the limit will exist if I take that 0 out? Not necessarily. I don't know. We'll see in a minute. In this case, the answer is yes, though. Okay, so limit. Do not drop the limit operator. I cannot do anything to the top, but I have to remember how to factor the denominator. I already know that it has to have a factor of x plus 2. So this is a sum of two what? Sum of two cubes. Good. So x plus 2, and this is the trinomial. What is the trinomial here?
So x squared minus 4x plus 1.
Careful. Minus 2x plus 4. Yes. So let me refresh your memory on the formula. So a cubed plus b cubed. Please remember it. Write it in your notebook, etc., etc. It's a plus b, a squared minus ab plus b squared. And if we do factor the difference of cubes, the binomial gets the difference and the trinomial gets the sum. We never discussed the last term that is always positive no matter what. So this is how we factor the difference, the sum and the difference respectively of cubes. So that's why we get x squared minus the product of these two plus the second term squared, which is 4. Okay, and now I'm happy for what I see. What do I see? Well, I see this. Now at this point I can drop the limit operator once you tell me the final answer. And the final answer is 4 plus 4 plus 4.
12.
Exactly. But it's 1 over 12. Any questions? Any questions on this? Okay, moving on then.
Wait.
Yes?
So you were able to do the sum of the trinomial because the 8 would go down to 2 to the third. So equivalent for
Say it again. Are you talking about from here?
just for like underneath where you have like A plus B.
Where you broke.
Yeah. So that would
So
be.
if it's the sum of cubes, I have the sum and the difference.
And
If
you
it's a
got that-
difference, I have the difference and the sum.
And you got the B from if the 2 to the third would be 8, right?
So you mean this b?
In the original problem, x to the third plus 8, he's saying that would become 2 to the third, and that's why you get to use.
Yes,
Okay.
yes. So this is x cubed plus 8 will be x plus 2 and x squared minus 2x plus 4. Because x cubed is x cubed and 2 cubed is 8.
Yeah.
So then this follows the pattern. So the first term squared minus the product of the 2 and plus the second term squared. Is this okay?
Yeah.
Okay, perfect. So let's move on because the absolute value has a difference anyway. So let's look directly at that, and then you can choose other problems, of course. Feel free to do that. So limit as x approaches 0 from the right, from 1 over x minus 1 over the absolute value of x. In this particular situation, we have to simplify the function fully before we determine any limit. So forget about the limit for now. We are given a function f of x, which is 1 over x minus 1 over the absolute value of x. And we will start with the absolute value of x. Does anyone remember the formal definition of the absolute value of x? Very good. Excellent. Great job. This is indeed, thank you, Hannah. This is indeed the formal definition of the absolute value. Like with what we did on the first day of classes, if you remember, I said you only need the pattern. You don't need A and B. So the same thing here, right? I should have written first term cubed plus second term cubed is first term plus second term times first term squared minus the first times the second plus the second term squared. Same thing here. You're not going to be given all the time just plain x. You may be given any expression. So how we remember this, the formal definition of the absolute value is this. Any expression you may be given x, but most probably not. So any expression. So notice that there are 5 situations in which we have the same thing. We copy this 5 times. The only difference is here. If you solve this inequality, you do not have to solve this one. Whatever you get here, the opposite is this. So if this one is an example is x greater than or equal to 4, this one must be x less than 4. You don't have to solve the second inequality. It will be a waste of time. Okay, in this example, we just have plain x. So I'm building the function step by step. So I only have built this. Bless you. Now I want to determine this. Then I will put the negative with 1 over x in front, and then I'll get the entire function. But first I need to determine 1 over x in absolute value. So how will you simplify this? When the absolute value is x, what do I get?
X is constant.
1 over x.
Sorry.
That's okay.
Then
When x.
greater than 0.
Excellent. Why? How come that I don't copy equal to? Excellent. Great job. Good. What is the other option? Excellent. Negative 1 over x. We're talking about 1 over the absolute value when x is. There is no discussion there. And now I can build the entire function. So the entire function f of x is 1 over x minus 1 over the absolute value of x. And now, please tell me what to write. I have this piece. This piece has 2 options. That's why the whole thing will have 2 options. I have to copy 1 over x. I have to copy minus. And what do I copy now? 1 over x for x greater than or equal to 0. I copy 1 over x, which just does not change. I copy minus. And then what do I copy for x less than 0? Excellent. One more step. Can anyone give us the top piece? How much is this? You have an apple, you give it to me. How many apples do you still have?
0.
Good. I know it's late. I have to entertain you with apples or something. Okay, and what is 1 over x minus 1 over x? How much is an apple plus an apple? 2 apples, thank you very much. So what happened here? Well, we only simplified this function fully into 0 for x greater than 0 and 2 over x for x less than 0. And only now I can determine this limit. Limit as x approaches 0 from the right. Which branch? Only one.
Bottom.
So the limit is? We just use the limit law that says the limit of a constant is the constant when x approaches anything you want. Questions? And here's another question that I have for you. How come that I did not write limit of this minus limit of this? I could have written, we just discussed limit laws, limit of this minus limit of this. How come that I didn't?
one of them isn't a number. So that would
Right, it's undefined, right? Or infinity. So the limit of 1 over x, remember the graph, as x approaches 0 from the right, is infinity. I can't split. I can't use the limit law because the assumptions were that the limits for both functions exist and they're numbers, in other words, right? Good, perfect. Any questions on this? Any questions on this? Okay, so let's talk about squeeze theorem. Some time ago, I gave you a handout with a long, long list of limits. Can I borrow it for a minute?
No.
Okay. I would like you to work on few of them already. This handout. Even if you don't have it, that's fine. I'm going to write it here. So I would like you to work on number 1, again on number 2, on number 3, on number 6, on number 7. I want to work on number 9 together. And number 12. So 1, 2, 3, 4, 5, 6 for next time. Thank you. Sorry. Okay? And tell me your answers. In the meantime, because I want us to finish that handout. When we get the chance, it's not everything will be discussed right away. So you're going to see, we're going to go back to it. Okay, so the squeeze theorem. So here is a graph. I like the graph from the book very much. I will graph the same thing, so it's better if I just show you this graph. How do you put controls here when I have to put the book and stuff on it? I mean, how do you? I have no idea. Okay, here it is. Now I have to lift the book, and if I lift the book, it's not going to zoom in. And okay, it did it. Perfect. So this is a function. Look at it. It's x squared. This is a function, x squared. And here's another function, right? It's negative x squared. They both have the vertex at the origin. This one opens up because the leading coefficient is positive, and this one has a maximum because the leading coefficient is negative. And here is a third function. So the green is one function, the blue is another function, and the red is a different function. Sometimes, and I'll show you an example in a minute, sometimes it's very difficult or impossible for me to determine the limit of the red function as x approaches, let's say in this case, in this example, 0. It doesn't have to approach 0. But let's say it approaches 0 from the left and from the right. If you look at the graph, you'll say, oh, but look at the graph, it's 0. True. But we have a theorem that helps us here with this situation. And we say that this function, the red function, is squeezed or sandwiched between the blue and the green near A. I don't know, this red function can do this now. I don't care. But near this value, near 0, in the vicinity, we say, in the vicinity of 0, the red function is squeezed or sandwiched between the green and the blue. Okay, so there are certain conditions and hypotheses here. Okay, so I'm going to graph a little bit because I want you to have it together with what I'm going to write. So here is the green function. So this is, let's say, it's x squared. And here is the blue function. Let's say it's negative x squared. Because I want you to have the graph in your notes, or I should have the graph in my notes. Okay, so this is a function f of x. That is obviously by the graph sandwiched around 0, near 0 between the upper bound x squared and the lower bound negative x squared. So the first hypothesis is that I show that f of x is squeezed between g of x and h of x. In this case, the bottom one is negative x squared, the other one, the top one, is x squared. So I have to show that it's squeezed. That's the first hypothesis of the theorem. I have to show you somehow that I have a lower bound and an upper bound for this function, for a function f. Here's the number 2. I have to show you, I have to convince you that the limit of g of x equals the limit of h of x, and they equal, let's say, L. Both functions have a limit as x approaches a from either side. Furthermore, both limits are the same number. And then I will say from 1 and 2, what do I conclude? That the limit from f of x as x approaches a by the squeeze theorem equals L. Excellent. I have no way of determining this limit. You'll see the situation in a minute. But if I show that it's squeezed between two functions, and if I can determine the limits of these two, and they both exist and they're both the same number, then I will immediately conclude that based on these two hypotheses that are fulfilled here, then the limit must be the same. Okay, so let me start with an example in which we don't even have the function. We don't even have this function. So, and this is problem 38 on page 107. And here is what we're given. We're given 2x less than or equal to g of x less than or equal to x to the 4th minus x squared plus 2. It says for all x, we're asked to find the limit of g of x as x approaches 1 from either side. Now, I hope you agree that what we are given is the fact that the function is squeezed between two functions. Not just near a point, but for any x. This function, g of x, is squeezed between function 1 and function 2. And this is the first hypothesis of the squeeze theorem. So this is already given to us. We do not have to determine the function from below and the function from above. We are given that. We're given that the function from below is 2x. The function from above is x to the 4th minus x squared plus 2. And we have g of x somewhere in between. This is the first hypothesis. Now, I have to check the second hypothesis. What is the second hypothesis? I have to show that, or I have to determine what? Yes, the limit of 2x when x approaches exactly 1. Thank you. And the limit of x to the 4th minus x squared plus 2 as x approaches 1 is exactly, first of all, let's see if they exist. Good. What do we do with 2x? We had an example a few minutes ago. I mean, not a limit law a few minutes ago. We said that the constant goes in front. And then how much is the limit of x when x approaches 1? How much?
2.
Yes, yes, it is. The whole thing is 2. Correct. Perfect. What about the limit of the second one? Excellent. So then what do I conclude from 1 and 2? By the squeeze theorem. How much is the limit of g of x that I don't even have when x approaches 1? How can I determine a limit of something I don't even have? As a typical example for squeeze theorem, this must be exactly. If the function is squeezed between 2x and that x to the fourth blah blah blah, and the limit of both is 2, then the limit of the squeezed function must be 2. Okay, one more example here. Let's look at, yes, 39. So we're asked to find the limit of x to the fourth times cosine 2 over x when x approaches 0. Okay. We're asked to find the limit. What do we have to do first? Plug it in. Very good. So this is a product of two functions. This is one function and this is the other. Of course, this one it's a function composition because it has another function inside it. So let's start with this. When x approaches 0, where does that go? Very good. I have to start from the inside of function cosine. When x approaches 0, where does 2 over x go? Exactly. But you could say, oh, wait a minute. 0 times d and e, 0. No. We can conclude that. And you will see later, and I want to give you the heads up. We know that a number divided by 0 is called, that fancy word, undefined. But there are 7 indeterminate cases that we are going to see throughout the semester. Not undefined, indeterminate, 7. We already saw the first one. This is an indeterminate case. What does that mean? It can be anything. It can be 0. It can be 1500. It can be 1,000,000. It can be e to infinity. It can be anything. It's indeterminate. We can conclude. We have to work on it step by step. That's why we call it indeterminate. And there are 6 more. And as we progress through the semester, I'm going to add to the list. So this is, again, something for your little notebook. Okay, so we're back to our problem. I will have to start with cosine. Why do I start with cosine? Because cosine x, in this case I have cosine 2 over x, but I just want to talk about cosine for a moment, is a bounded function. It doesn't go to infinity and negative infinity. It's topped, we say bounded. From above by what? Excellent. And from below by? Excellent. Great job. This is in general. What we have here is cosine 2 over x. Any cosine of anything is bounded between -1 and 1. So remember, the function is a product. I already have, don't erase anything, I'm just making a point. I already have discussed this. But that's not sufficient. The function is not just this. The function is this product. So how do I get this product in the middle? How do I get an x to the fourth here? I multiply everything by x to the fourth. Now careful for a second. X to the fourth has to be a positive number. Because otherwise what happens when I multiply an inequality, both sides, 3 sides in this case, by a negative number? Right, I don't know. Okay, but is x to the fourth a positive number forever? Yes. And it cannot be 0. So I already wrote that. It cannot be 0. Is that true? Yes. How do I know? Because this specifically says x does not equal 0. So I'm safe. This operation is safe. So indeed, I multiplied all three sides by x to the fourth. It was strictly greater than 0. Now I'm happy because I have right here in the middle, I have my f of x. That whole thing is f of x. What will this be then? And what will this be then? Yeah, I could name them the whatever you like. It doesn't matter. So we used f for the function. It doesn't matter. So I already showed the first, I would check the first hypothesis of the squeeze theorem. I showed that the function is indeed squeezed, sandwiched between two functions, one from above, one from below, near 0. I don't care about anything else here, just near 0. Now I have to show the second step, or the second hypothesis. What is the second hypothesis? That if this doesn't work, then I'll say squeeze theorem is not applicable here. I can't draw a conclusion. I can't apply it.
f of x, its limit has to be equal to
So I have to find the limit from,
gx.
yes, negative x to the fourth when x approaches. Good. And I have to find the limit x to the fourth when x approaches.
0.
Good. If these happen to exist, furthermore, if these happen to be equal, then I will conclude that the limit of the function that is squeezed between those two must be, by the squeeze theorem, must be equal. So what do we have? What do we have?
0.
Good. From 1 and 2, we conclude by the squeeze theorem that the limit of x to the fourth cosine 2 over x as x approaches 0 from either side has to be
0.
Has to be 0. Great job. I know I have 7 minutes left, so I would like, I don't want to start the new section in 7 minutes. So we're going to hopefully complete 4 and 5 on Thursday, and 6 and 7 next. Yes, and that's, and 7 and 8 go together. So we'll see. I'm hoping that we are on track for the first test. If we need more time, we'll get more time. Okay, so please choose another limit. I would like to pick a limit now that has addition of or subtraction of two terms. Like, for example, maybe 28 or maybe 26. Any preference?
You got about 28 here.
28. Okay, fine. 28. You may have time to look at 26 and 28. Okay, so in 28, we have limit as h approaches 0 from 3 plus h to negative 1 minus 3 to negative 1 divided by h. Okay. What does 3 plus h to negative 1 mean?
Isn't it 1 over 3?
Of course, thank you very much. Of course. Please remember that. Any negative power means 1 over the base to that positive power. So we're back to the problem we looked at today, but the problem we looked at today in that quiz, you don't have to turn it in. Obviously, it's way more, requires way more work. So the same thing. I know when I plug it in, what do I get? My hope is, yes, and I do get 0 over 0. So I know that somehow what has to be eliminated if the limit were to exist? What factor of h minus 0 or h? Good. So the least common denominator, do not drop the limit operator. The least common denominator in the numerator is, careful, these have nothing in common. They are two different factors. They are like prime factors. So the least common denominator is, excellent. Adjustments, as I like to call them. Again, if you know a different method, do not change to mine unless you think it's easier. What is the adjustment for the first one? Good. What it does not have in the denominator. And what is the adjustment for this one? Can anyone give us the numerator, please, step by step, slowly?
9 plus 3.
So this is 3, and this is minus 3, and this is minus h. Any questions about 3 minus h? Do we all see it? Mario, you see it?
No.
Okay, so 3 times 1 is 3, minus 1 times 3 is negative 3, minus 1 times h is negative h.
Okay.
Better?
Yeah.
As expected, all terms without h go away. Do not drop the limit operator, please. You can't, you're not allowed to, not yet. So limit as h approaches 0, negative h over 3 plus h times 1 over h. Please put brackets. Of course, this is the second step. What has to happen? Mandatory. Of course, they simplify. Good. Now, only now you can drop the limit operator. What is it? Only when you give me the final answer. Very good. As h approaches 0, 3 times 3, negative 1 over 9. Is that okay? Okay, we have 2 more minutes. At least let's get this one started. I promise I'll stop in 1 minute. So, and please finish it up at home. 26 on 107. You have those 5, 6 problems and this one. It's one of them. I'm pretty sure I copied this because I like this. Can I break it up? I want to write the limit of the first minus the limit of the second. No. So what will I do? What is my first step? I can't because it's undefined. So I need, in this particular case, I need one additional step before I plug it in. Yes. So now please just give me the least common denominator. I'll stop. That's it. Good. I promise to stop. Please finish it up.